context of locomotion. And Dan Goldman from physics at Georgia Tech is going to tell us about swimming through sand.
Right. Thank you. Thank you to the organizers for inviting me to be loud in the back. Thank you for the organizers very much for the honor to come and talk to you. I apologize I didn't join you this morning and in previous weeks, but I've been working on the other parts of research, which I don't think one talks about too much until one actually has to do it, and that's writing endless proposals to try to get money to fund all the research I will, or some of the research I will tell you about today. So I'm at Georgia Tech. I'm in the School of Physics. Also have adjunct status in bioengineering. And much of the work that I'll tell you about in the 3 lectures was done, as much of the biological work was done by a bioengineering student in my group. The physics work that I will tell you about is done by physics PhD students in my group. And that's clear as we move along. So the title of my lectures is Swimming in Sand, but I think that it's more broadly lectures on really the mechanics of interaction with granular materials, including biological and physics experiments, numerical, theoretical, and physical robot models. It's a mouthful. I'm an experimentalist. In my group, we mainly do experiments, but we also do some modeling in the ways that experimentalists do it. And I hope to show you different modeling approaches today that are allowing us to make some progress in these kinds of problems. This is a little movie which I will talk about probably beginning tomorrow. Okay. I first want to start out though, this is the animal that we're talking about, a cute little lizard called the sandfish, which does remarkable things, which again you'll hear about more in gory detail over the next 2 days, 3 days. But I want to start more broadly to give you kind of a sense for what we're doing in my group in the context in which we're operating. And that's the following. So, as I'm sure you know and have learned in the last several weeks, interaction with fluids are beautiful and rich. And in the locomotion world, there's many examples of organisms, and not models of organisms, but devices which move in fluids like water and move in fluids like air. And of course, the mechanisms behind the thrust and lift production in these kind of these organisms, as well as the devices, are fascinating, and you can read about these, of course, in Goldman's beautiful book, as well as other sources. But in some sense, the problem is solved in some way. We can write down the Navier-Stokes equations, and we can supplement those equations with the appropriate moving boundary conditions. They might be ridiculously complicated, as in the movement of the wing of a bird, and maybe less complicated in the relatively the little movement of an airplane wing. But in principle, we could compute all lift thrust forces, knowing simply the geometry and the mechanical properties of the locomotor and the viscosity and density of the fluids. And you can get also sort of exciting examples like this, which I'm sure you've seen. This is 2 papers on this, the beautiful work of Leshy McMahon, as well as Shea and Lauder. And this is, of course, a lizard that is interacting quite well with a fluid, water in this case. This is the Bacillus, the Jesus Christ lizard. And this lizard can run pretty fast over water. It turns out that the juveniles in this species are better runners. This work showed that basically they can generate double their body weight to keep themselves aloft, whereas the adults can only generate about 1 time their body weight. And this, people speculate, allows for large populations of these animals along riverbanks, because when the large ones want to eat the small ones just run away across the water and the large ones can't follow. So, beautiful, interesting interaction problems. But again, in principle, we can understand the intrusion of this foot and the hydrodynamics which generates the lift and thrust forces to allow it to move so spectacularly. In contrast, there's a whole lot of organisms, I picked a bunch of pictures here, which move around in what we call the terrestrial environment, meaning terra firma, or what we sort of think of as terra firma. We as humans tend to think, I guess unless you're mountain biking on dangerous slopes. We tend to think that, that the terrestrial world is sort of a boring, rigid, flat, vaguely hilly place. Again, I'm just sure not going off-roading. But to most organisms, the terrestrial world is a world of tremendous complexity. Well, at least we think it's of tremendous physical complexity. Imagine the challenges of pulling a several hundred kilogram, I guess, cat up some tree bark, which is delicate and can rip, or a little crab that runs up a tree heel, or a gecko which manages to stick to basically even atomically flat, smooth surfaces using van der Waals interaction, snakes that move in the desert, cheetahs that run over land, these animals which reach ridiculous heights. The terrestrial world has a diversity of substrates that organisms have to encounter, and in fact organisms have engineered a diversity of solutions in the last several hundred million years during the conquest of land. Here for me is a video which I think basically I can show and then leave because this is for me my career if I can understand the locomotion that goes on in this video. So can we dim the lights maybe here? This one is good. You can pay no attention to the rest of the talk. This one's good. Ah, how about that? Good. Okay, so watch this. So here's a lizard, and this is of course courtesy, a student of mine. I don't just say you got it, you recorded it. Here's a lizard. A lizard is searching in a complex environment for some little rodent type thing, which then takes off. And if you watch this video over and over, you can see basically every kind of interesting, complex mechanical interaction that you can think of for terrestrial locomotion. Well, there's flying. There's a lizard breaking a substrate, full of fascinating challenges, the mechanics of materials. There's the animal hopping and deforming the material as it hits. There it's going to suddenly skid, I think. There's a slide as it barrels away, and there's the lizard doing the same thing, traversing gaps, traversing obstacles which are large compared to its hip. And in this case, the lizard doesn't get its prey and the animal runs away. By the way, there's also very interesting motion planning, path planning type challenges here, because it turns out that this animal knows where it's going. It's set up sort of a maze of trackway that it can maneuver and escape nasty predators like this. So in this video, we have a huge range of interaction of matter and complex materials. The matter happens to be biological, and the complex material happens to be the kind of terrestrial environment. Now, the major challenge, of course, is that much of these interaction events, these seemingly simple interaction events, like the limb of this little rat scraping against this material, are not described by the kind of partial differential equations we have for fluids. In fact, we don't have typically partial differential equations to describe them at all. So if we want to try to understand this locomotion, we have to resort to other techniques, and that's what I'm going to basically tell you about. But that's the kind of big picture in all this business. I'll give you a few more big picture things. For me, in particular, the flowing terrestrial world is of fascination. So here's 3 examples that I just happen to like. Here's a little lizard. It's sitting on a bunch of leaf litter, and the little lizard suddenly takes off after being scared by an experimentalist, me, and makes the material yield and flow as the foot thrusts back under its force. Here's another example of animals kind of careening over rubble with rain. And here's a very interesting and sort of terrifying example to try to think about how to understand from a fundamental point of view of interaction, movement on snow. Little is known about the principles of movement of organisms on these types of grounds, and the physics of interaction of these grounds is really interesting. Yes, and please, by the way, interrupt me at any time to ask questions or to tell me I'm wrong. Or that kind of thing. Yeah.
What was the source for the mouse and lizard movie?
It's BBC. We can talk after that. We can talk after. Yeah. Okay, by the way, these questions also, I think, have interesting relevance to the earliest tetrapods, the earliest animals to walk on land. Here's the kind of Wikipedia version. Here's the Wikipedia version of all these crazy looking things that were living 400 million years ago, tetrapods, four-limbed animals, as they emerged over billions of years from swimming, from only having to generate thrust and lift to move themselves through Newtonian Navier-Stokes fluids, the fluids described in Navier-Stokes equations, to sort of using these appendages that were basically designed for thrust, in the water to actually allowing themselves to lift them, allowing them to lift themselves on materials like mud, sand, and all these complicated, nasty materials that we don't have physics for. So understanding these interaction problems can potentially lead us to generate testable hypotheses, or at least testable in models of the evolution of limbs of early animals. Okay? The final sort of big picture movie I guess I'll give is one that is of particular relevance to the animals I'll talk about next time. And that is a flowing environment which looks barren and lifeless and not very interesting, but in fact houses a huge amount of ecological diversity and interesting locomotion interaction problems. These are the desert sands. This happens, I think this might be the Danube, I don't know where. But in the dry deserts of Africa, for example, alone, people have counted there sort of 100 species of lizards and snakes, and about 10 to the 3 invertebrate species, things like ants, beetles, and scorpions. And they all live in these kind of environments which look basically like homogeneous and not very interesting. But the physics of these materials allows these organisms to do very interesting things. So here is an animal, a sidewinder snake, which is after its prey. And it's going, and what's it looking for? A little lizard. And it sees a little lizard and starts hauling after it. But the lizard is very smart and uses the properties of the granular material, the fact that it can behave like a fluid and a solid, to bury inside. And then the animal gallops across there, sidewinding away, and the lizard is not fooled and just goes and dies underneath. But the snake has been doing this for a long time, and the snake knows that the only strategy that will work, since it can't outrun it, is to trick it. So it does a particularly fascinating burial process, in which it buries its body, even the head, and then does something sort of amusing, which is to stick, you'll see in a second, its tail up. Why? Well, lizards don't particularly like sort of stiff tails sticking out of the ground, but ants think they're plants. The ant goes to the plant, the lizard goes for the ant, the snake goes for the lizard. So that's the motivation, this is the name. So that's the motivation for me in my group and why we're interested in these kind of terrestrial locomotion problems. And I will tell you right now that they are hard, and one of the reasons they're hard is, of course, the biological experiments, which is my love and what I like to do, but as well as the modeling challenges, and that's what I hope to sort of show you how the kind of progress we're making today. Okay, so here's what we do. We call my lab, the students call it the crab lab for complex rheology, studying all of interesting materials, and biomechanics. At one point we were studying these dose graphs. We haven't been doing so much with them recently. But we study a diversity of organisms that all perform tasks well on a granular environment. This is what I'll talk about. We study physical models of those organisms, what you might think of as robots, but we think of as very useful models which interact with natural environments that we don't necessarily then have to model. And we also do some physics of these materials, granular physics. Okay, so here's what we're going to talk about. I'm going to give you an introduction on general principles in terrestrial locomotion because I think that without it, the context in which I'm telling you things makes little sense. We'll then talk about the kind of main player, the main substrate we like to study organisms and models of organisms on, granular materials. I know you've already heard about it, some probably from Pecco and some from Heinrich Jaeger, but I'll hopefully not bore you with repetition. I'll then talk about a particular example of what we're calling localized intrusion in granular media, which is a source of problems which is directly relevant to the kind of interactions we study with our organisms and our robots, and which are, at this point, I'd say, largely undeveloped theory and modeling approaches for these. And along the way, I will tell you about the kind of modeling approaches that seem to, at this point, be giving us some quantitative predictive capability for our organism and physical modeling studies. They're called discrete element modeling and resistive force theory. Again, I'm an experimentalist, so we use all these modeling tools and theory, and put theory in quotes, in a kind of way that works well enough, but those with a theoretical bent, we'd love help on these kind of problems. So that's my other sort of pitch while I'm here. This will probably get through some chunk of lecture 1. Lecture 2 will be more of this modeling, as well as beginning of the biology of the sandfish and how it actually does what it does. And we'll start into the modeling approaches on the sandfish. And then the last thing I'll talk to you about is some of the most recent work we've been doing. In fact, that's actually using the models to make predictions about the biology of the organisms. And we're having some good success with that, and I hope to tell you about it. So that should be it. Okay. So, point 1, terrestrial biomechanics. I have to sort of tell you kind of what has been the state of the art, because it leads to sort of a way to think about how to approach these kind of locomotion problems. And principles in terrestrial biomechanics have been discovered by reducing the complexity of the substrate interaction. So here, for example, is an animal, and what you do is you don't study the animal out in its natural environment. You bring it to the laboratory. In the laboratory, people typically create level, rigid, high-friction trackways. They scare the animal at one end, the animal runs across the trackway, and using the techniques that I'll tell you about in a second, they can understand something about the mechanics of how the organism is moving. The most famous place for doing this, of course, is the Harvard Concord Field Station, in which people like Andy Bueter chase things like elephants and using this sort of crazy stuff across the ground. In my lab, we're on the smaller scale, we chase elephants. Okay, the kind of main workhorse in this field, the last, I don't know, 50, 40 years, has been what people call a force platform. And what it does is simply measure the ground reaction forces that are generated as an organism steps onto the plate. The organism applies force to the plate. Third law, the plate then applies force to the organism to propel it forward. Here happens to be a low-cost, under $200 force plate that we built in my lab. And it just looks like a big, it just looks like a big platform. And I won't go into the gory details, but it turns out that underneath this platform, here's a kind of cartoon view of it, a plate, are 2 beams, little posts, which bond this plate to basically a kind of rectangular set of beams. And on those beams are bonded little strain gauges. And strain gauges are devices whose electrical resistance changes upon deformation. Now the electrical resistance changes are small, and you all may remember the Whetstone Bridge from electronics class or from some derivation, which then allows you to take the electrical changes in resistance and basically do a difference measurement and detect small changes in resistance, which allows you to detect small changes in the flexion of the beams, which is good because then you can bond your plate to relatively stiff beams, and as your elephant or your human or your whatever steps on the plate, you don't get large deformations in the structure. So, okay, so that's the sort of basic technique. Here's kind of what it looks like. Here's a strain gauge on it. Talk to me afterwards if you have any questions, or you can read about this endlessly. People do this on the human scale, and just to show you that it works, here's my student Nick Ravish, who built it, running across the force platform. And this is a video which is taken with a high-speed camera, which 10 years was $50,000, and now is $200. And so one of the beautiful things about this area of biology, biomechanics, is that you can do experiments on all sorts of weird animals and in all sorts of weird locations for relatively low cost, which is nice. So okay, so you take your high-speed camera, let me play it again, and you film student running across, and you measure force, and the red curve is the normal force, and the blue curve is the force, what we call in the fore-aft direction, the direction of motion. And the convention here is such that if he pushes down on the plate pushes back on him, as you might expect, supporting his weight. In fact, you can see that it even basically doubles his weight as he goes across the plate. It doubles the weight, the dash line is body weight. And in the fore-aft direction, you get sort of an interesting pattern. You get that as he steps onto the plate, the force spikes negative, meaning it turns out that the force is pushing him this way. He's applying a force to the plate, the force is accelerating him back, and then as he goes through his step, the sign switches so that the ground accelerates him forward. And so that's what happens at each step during a run. I should say that this, during a trot in this case, I should say this is quite different than walking, and if you're interested, ask me later. But it turns out that you can do this not only on human scale, you can build little tiny force platforms with also strain gauges. It's an incredibly useful experimental technique in this field. Basically, bond strain gauges to anything you can, and if you are skillful enough, you can measure small forces. Millimeter resolution here, we made them for even cockroach scale locomotion. And of course, you can film them simultaneously now. And so then you can get kinematics, how the limbs and the body move, and you can get at least center of mass dynamics of an organism as they walk, trot, or gallop across this force platform. And something kind of interesting has emerged from this, from 50 years of doing this. And what people have discovered is that whether you're a 6-legged cockroach, a 2-legged human, an 8-legged ghost crab running sideways, or a 4-legged dog trotting, basically, the kinematics all kind of, if you blur your eyes, look more or less like this kangaroo. More or less like this kangaroo. And what do I mean more or less? I mean that at mid-stance, when the animal is stepping, or the human is stepping, the center of mass is the lowest, and then it sort of moves away. And the forward speed at mid-stance is maximum. And again, this is different than walking. It turns out when you walk, I'll just say 2 seconds on it, when you walk, at mid-stance, your center of mass is at its highest point. You're basically, when you're walking, can be described kind of like a pendulum, an inverted pendulum on it. You're falling over. When you're running, people describe this by what they call the slip model, the spring-loaded inverted pendulum, because the kinematics, at least, tend to resemble a pendulum, a pogo stick, which has this kind of motion. Okay? Well, it turns out that it's not just the kinematics, which are as you might, seem to be invariant across organisms. As you might expect it from the kinematics, the force pattern for the center of mass is also independent of morphology. And I didn't show you any real experimental data here, I just simply sketched it out. But what one finds is that for all of these organisms, whether you're a cockroach or a kangaroo, during sufficiently fast locomotion, the vertical force has this sort of characteristic shape that I showed you earlier, where it peaks at mid-stance to some multiple of the body weight, and the fore-aft force first goes negative, then goes positive as the organism first decelerates and then accelerates. And you'll see that there's no scale on here, and the cool thing is that you can basically take a cockroach and you can take a kangaroo, and the force pattern looks very similar. And so people have done one more thing, which is pretty clever, I think. Well, very interesting, in the sense that you can record the maximum force on the ground, and you can get an estimate for how much the center of mass compresses as the organism lands on the ground. And you know the body weight of the organism, and you know basically the limb length. And people have found that if you make the following plot, this is a non-dimensional sort of spring constant. You take the maximum force on the ground, you divide by the weight, you divide by the amount that the center of mass compresses, and you divide that by the length of the limb and the number of legs, and you plot that on a log plot. As I say it, of course, it sounds more crazy, but you plot that on a log plot over 6 orders of body mass. This K value, this sort of virtual spring constant for a limb, seems to be roughly independent of body mass. So not only are these organisms all kinematically resembling kind of a pogo stick, they all seem to have basically the same kind of spring, virtual spring embedded in them. And nobody really knows why yet. There's some recent work by Phil Holmes and his collaborators and students analyzing kind of pogo stick-like models, which gives some indication that there might be some stability benefits to moving around with a virtual spring of this value. But no one really, I think, at this point has a good theory. Yeah?
So does the previous thought mean that everybody spends a little bit of their energy breaking?
Hmm?
Breaking?
Yeah. So this is a good question, which I should have said. That one of the kind of ideas that people have for at least walking, let me start with walking, is that it turns out that if you get walking and you start walking in a sort of inverted pendulum, then you can basically, if you don't lose any energy upon collision with the ground, you can basically start the system going and you remain conservative for the entire duration of the walk. So you're basically trading kinetic energy of moving forward with potential energy of rising and falling. In a similar way, people think that larger organisms, at least, exploit this kind of energy trading when they're running. So that if you're a kangaroo or a human and you hit the ground, you basically load up an elastic element in your limb, which happens to be tendon, and that stores some potential energy, elastic potential energy, which is then released upon the next step. And so that's the thought of why you bounce when you run. It turns out that people have measured this, that things like cockroaches, in fact, don't store any of the energy. All the energy basically gets dissipated as they hit the ground, and then they have to re-excite to push forward. But still, they seem to mimic this kind of dynamics. Does that answer your question? Okay. All right. But it's not just, and we're getting back towards hydrodynamics soon, towards granular media, but I just want to give you kind of a picture here. It's not just kinematics and dynamics in what people call the sagittal plane. This is interesting. It's interesting, the plane that you and I and kangaroos and dogs operate. But in the horizontal plane, where I think 3/4 of all animal species spend most of their time, stability is very important. And so let me just show you this. It's sort of an amusing video, but makes the point. Here's a cockroach. This is slowed a lot. And we tripped it with a wire. And you see that if you are unstable in the horizontal plane, you can go careening out of control very easily. This happens to be, we exaggerated the trip by coating this plane with some stainless steel. But here you can see that the animal took some time, some graphite coated stainless steel. Here the animal takes some time to recover after it gets a significant perturbation. And in fact, people have made, in my opinion, the most progress in terms of the kind of locomotor understanding from a theoretical point of view of exactly this problem, which is why I wanted to bring it up. And it sort of followed from this observation. People did that same experiment I just showed you in a much more controlled way, in which they strapped a cannon to the back of a cockroach. This is the cockroach running at you. Here's the cannon, and it fires and gives it a lateral perturbation of some impulse, which is comparable to the momentum of the animal moving at you. And it turns out that on level, rigid, no-slip ground, the animal recovers quite rapidly, which within 50 milliseconds, which is fast. And at the time, people said, well, it challenges the fastest neural reflex. I'm not sure that's exactly true, but it's still a very fast recovery. And here's some plot showing the lateral velocity of the cockroach that gets disturbed here, but within a short time, the animal's back to doing this kind of locomotion. And it turns out that when a cockroach runs, it runs in a way that is sort of interesting. This is slow video, slowed 20 times, and you're looking over the back of the cockroach. And the cockroach uses 3 limbs to move in synchrony. 3 limbs in synchrony move. And it basically sort of moves back and forth side to side. It's a little bit hard to see. If you measure, for example, using a force platform and ground reaction forces, you'd see not only acceleration, deceleration in this direction, or forward direction, but also acceleration and deceleration in the left and right directions. And it turns out that Phil Holmes and John Schmidt made the first models of this, where they imagined, just like the kind of slip model is a virtual pogo stick for an animal running on the sagittal plane, this vertical plane, they imagined the sort of virtual limb for this cockroach, and they call this the lateral leg spring model, such that when the cockroach touches down with 3 limbs, you can sort of imagine a virtual spring contacting the ground, which compresses and then re-accelerates the cockroach left and right, and on and on and on. And it turns out that this is a purely conservative model, and if you give this the right parameters and give it a little bit of an energy initially, it just sort of bounces to the left, bounces to the right, bounces to the left, and bounces to the right. And then they did a cool thing. Because it's a simple model and not a very complicated organism they can analyze, and they essentially wrote down Newton's equations for the translational and the rotational degrees of freedom. And they said, okay, well, I'm going to now write down a return map, because I'm only interested in sort of step to step, what happens at each step. And they could then write a map that linked the forward velocity, the heading relative to the velocity, the angle of the body in the roll frame, and the omega, which is the rate at which the body angle is oscillating. They could map that at step n+1 to step n. And this is this map F. And it turns out that they could look at the eigenvalues of this, and they found that basically, even with this conservative system, if they gave it a perturbation here, for example, because of a trading of forward velocity and angular momentum of the the locomotor, they found that these variables, like this heading direction relative to the movement and the omega, displayed asymptotic stability. They found that the eigenvalues in this of this map were magnitude less than in a conservative system. And they made a prediction that said that, in fact, they could plot the eigenvalue and find the eigenvalue as a function of speed, and it turns out that this is where the cockroach lies. The cockroach seems to lie at the place where the eigenvalues are smallest. And the hypothesis then is that, in fact, what the cockroach is, by targeting this kind of dynamics where it basically bounces back and forth on this virtual leg spring, it's essentially acting like a conservative system which has passive stability, passive dynamic stability. Meaning that if it gets a perturbation, the mechanics of the system are such that they will correct the perturbation without any need for rapid nervous system response. And this is the idea. And in fact, this idea has been instantiated in a physical model. And this is a robot called Rex. And Rex basically acts like a slip, acts like a spring-loaded inverted pendulum in the vertical plane, and it acts like a lateral leg spring in the horizontal plane. And the cool thing about this robot, or physical model, we think of these things as, is that all the control is in the hip motors, and I'll explain more about this in a second when I get to granular stuff. But basically there's 6 motors in this thing, and those 6 motors' job is to keep these limbs whirling around in a particular pattern. And if the robot hits a bump, the passive mechanics of the system are tuned such that those perturbations are rejected, and the nervous system of the robot, the electronic control system, can then not have to worry about perturbations on a step-by-step basis, but sort of concentrate on longer time scale perturbations like where to go. So I think this is sort of a beautiful idea, and in fact it's led to a kind of approach, this is my last bit on this, which people sort of think of as a kind of neuromechanical approach to modeling organisms, and which your job is to look for what these guys call templates, which are low-order models of the dynamics of organisms, which the organism is possibly targeting for control. Meaning that all animals, when they're running, are basically targeting a slip for some reasons. Animals in the horizontal plane, which move a lot, which have significant motion in the horizontal plane, are basically targeting a lateral leg spring. And the idea is if you do that, there's good properties of those dynamics that emerge. Meaning if you get a perturbation, the system just automatically adjusts. And then the goal is to find what they call anchors, which are more complicated models, which then include things like morphology of the organism and information about the musculoskeletal system, and even information about the nervous system. And then the job of all these more complicated bits of the organism is basically to be controllers which target this kind of simple dynamics in executing behavior. So it's kind of an interesting approach, and it's kind of in the back of our heads as we think about the sandfish problems, which I'll tell you about shortly. But again, all of this work has been done with the idea, the experiments have been done, and the models have been done, that the ground contact is rigid, flat point contact interaction. Whereas, of course, in the natural environment, the cockroach encounters, things like this, which are significant deviations from the sort of slip-like template or a lateral leg spring template. And so then the goal is to try to understand if we can find templates, sort of simple patterns of movement on more complicated ground. Okay, so that gets us into the granular materials. Because here, in these kind of complex environments, lack of templates is a problem. So here's that robot that was running so spectacularly on hard ground, having a real challenge as it goes up complex. Right? It didn't hurt it. This is a robot called Rugged Rex, made by Austin Dynamics, and it's pretty tough.
Well, those are lousy legs for climbing a slope, I gotta say. You should put some little spurs on the bottom of it.
Well, it turns out that the spurs is an interesting thing. The spurs don't help you too much in granular environment. Because what happens is you engage with the spur, and then you're basically sliding grain against grain anyway. So yeah. So, I mean, this is a very simple, the limbs are passive. There's 1 degree of freedom per limb. We think we have some ideas on how to make better climbing robots, but the kind of challenges of surmounting a granular incline are interesting in some sense, because here, as you hit this material, basically you're causing an avalanche. And the steeper the slope is, the easier it is to trigger an avalanche. Okay, this is not just a problem for Rex. This is a problem all over the place. I just came back from the JPL, where I heard for a week about the problems of the Mars Explorer robots. And this is a famous video, which who's not seen this video? Okay, so this video is, it's either Spirit, maybe, I think it's Opportunity. One of the little rovers, the kind of this big rovers, was stuck, sorry, it was the bigger one. This big rovers was stuck for about a month. And so this video, all these shadows that you see are in fact time as Mars is rotating over a month or so. And this was a tremendous problem, and still is a tremendous problem. Of course, now the rovers are shut down. They lost contact with them. But they got a new one going up, which is the size of an SUV. And the same kind of understanding of how to make wheels move around on Mars is built into that robot as this. So these are tremendous problems that if you can understand just a little bit are worth billions of dollars. Yet, this is a very kind of well-known robot called a PackBot these days, which has been deployed in all sorts of environments. And these also suffer troubles in moving on granular substrates. These are two examples from our lab of little robots that have trouble in sand. So big trouble to move in sand. And just to give you a kind of sense for how hard it is, well, this could happen if you did have devices which could move them. And more broadly, I just want to say that these are problems of interaction in granular materials. And granular, these slides are not out of order, granular materials are commonly found in industrial applications. This got really out of order. Sorry. Let me get back to here. Sorry. Yeah. I just wanted to say one sort of thing about how we're learning to make robots and models move better on granular environments, inspired by what we're learning from organisms. Here is that same kind of Rex-type robot I showed you before. It's a smaller one which we keep in our laboratory. It's called Sandbot, and because it's wet in sand, I guess. And it has 6 limbs, and the limbs can basically rotate such that theta changes a function of time. And it turns out that the controller inside these limbs basically can set the angle of the limb to move in a prescribed trajectory such that the limb has a rapid fast phase and a slow phase, and then there's something like this when it jogs. You can see that the limb sort of whips around and then it's slower on the ground, and whips around and slower on the ground. And the nice thing is that you can tell the controller to change the relative proportion of the amount of the time the limb is in a slow phase or a fast phase, and so you basically have parameters that you can control this. And the engineers put this in because they found that certain combinations of parameters made the robot perform better in certain environments. And we got interested to test this in a systematic way. And so we did an experiment where we took the robot that ran so nicely on hard ground and we stuck it in a granular test bed that we have. This happens to be a big bed full of poppy seeds, but we can stick it in lots of granular materials. And this is sort of the limb kinematics that it was using, where it had a slow phase here, and whips around for a fast phase, a slow phase, and we can then set the overall frequency of this so that this motion is executed in a particular time, in a given time. And you see it goes absolutely nowhere. And one of the cool surprises in this, and we reported this in this paper, is that if we simply shifted the kinematics such that we started the onset of this slow phase at an angle advanced from the what we call the hard ground kinematics, the robot basically moves forward at a body length a second with almost imperceptible, well, you can't tell anything by eye, moving at the same frequency. It's just that there have been slight changes in how the limbs rotate as a function of time. So these materials are extremely sensitive to how they're loaded.
So does that mean something, if you're not exceeding the yield stress of the sand?
Yeah, so in fact, that's the simple picture is what happens, and this is sort of the video. And we have a little model which explains this. And basically what happens is that when the kinematics are set appropriately, the limb enters into the material, this will be play, and at some point the material locks up vertically. It has enough strength to hold the limb, and then what happens is that the limb essentially rotates within the cavity that's been formed and kinematically propels the robot forward. So the material is acting, and that's, sorry, this slide's got out of order. The material is acting in a fluid-like way as the limb enters into the material and then suddenly becomes a solid. And it turns out that the kinematics, which end up doing a good job of allowing this robot to move well on the granular substrates, are precisely those, and really only those, where this kind of timing is set appropriately. Yeah?
How does the ambient humidity affect this, if at all?
Yeah, it probably affects it. Probably affects it. We haven't tested that. All of this, I should say, is in dry granular materials where there is no interstitial fluid, such that interactions are only dissipative and repulsive. And I'll get to that in a second. But I think that it could affect it quite a bit. But this is then the essential idea that this material can behave like a fluid and a solid, and it turns out that when you maximize the material's solid time during a step, saying it kind of coarsely, the robot performs well. And you can then go and map out the speed of the robot as a function of these parameters, and only in a very narrow range of parameter space does the thing move well at all.
So did you
Yeah.
actually solve an optimization problem?
Yeah, so what we did is, and I don't have any of these slides here, but we can talk about it, is essentially we have a model which says that as the limb goes into the ground, the resistance force on the limb increases linearly with depth into the ground, which is a reasonable kind of model for these things. And at some point, the force is enough to support not only the weight, but any stresses associated with accelerating the robot up. Because the limb is translating at a velocity v, and as the limb, at some point, the material has enough strength to basically stop the limb and start the robot moving upward, which is set by the amount of speed, the velocity, and the time it takes to accelerate the robot up. So when those balance, you can basically solve for the depth of penetration, and then the depth of penetration, just from kinematics, since once the limb is embedded in the ground, is in this what we call rotary walking mode, that depth basically sets the amount kinematically that the robot's going to translate forward. And if the robot translates forward a sufficient distance, and that distance is basically the distance so that the next step it takes is not in a region which was previously disturbed by the first step, then the robot actually makes good progress. And so, not only do you have to solidify the material appropriately, you have to step over the material that you didn't solidify.
And how about the leg shape?
The leg shape, we haven't really too much for the leg shape. But, this leg shape is good for this sort of rotary walking mode. We've looked in another set of experiments at kind of a flipper-like appendages it penetrates in, which I'm not talking about either. This is just to illustrate the kind of fluid-solid properties. And then you can start to, when things go bad, the robot is basically swimming in this material, which has an incredibly complex rheology. So these are the sort of real-world nasty problems that these kind of things encounter, and we want to understand. Okay, so let me get back to, sorry, this got out of order. Let me get back to what we're talking about here. Granular materials. Granular materials I will define here as particles that interact purely through dissipative, repulsive contact forces, and for the purpose of the things we're doing here, are large enough so that any thermal effects, KT, is small compared to the energy it would take to transport a grain over another grain, so that's why you don't see gumballs popping out of gumball machines. It sounds like a trivial distinction, but the particles get smaller. Much more interesting things can happen, which we're not going to brush on today. By the way, I'm sure Heinrich told you something about this, Heinrich Gager told you something about this, but in terms of classification of granular systems, the word granular materials is used broadly to describe lots of different kinds of systems. Here are examples, some pictures I took from a very nice book, if you're interested, from Your Wood, called Soil Mechanics, a one-dimensional introduction. And here's a picture he has of, this is what we call beach shingle. So these are 100 millimeters. Here's sort of sand on a 10 millimeter scale. Here is clay, tiny, tiny little irregularly shaped particles. And I guess here is some more clay. Oops, disgusting sort of shapes. And we're going to be operating basically in this range, in the range of particles which are sort of 100 micron up to 2 or 3 millimeters. That's the kind of granular environments we are interested in, for reasons which will become clear when I tell you about our modeling approaches. And in fact, we're not going to think about any of the complexity associated with complicated particle shapes. Like Becco was showing in those particle sheets, stacking. We're going to sort of only think about nearly spherical, approximately spherical grains. And the most complexity in the grains will be that within a granular mixture, there can be what's called polydispersity, a mixture of sizes within a small range. Okay, so the cool thing is, of course, like I've alluded to, that these granular systems are a wonderful laboratory test bed to explore problems in the gas, solid, and fluid phases of matter. So here, for example, is a container of grains which we shook up and down, and it turns out that if you sufficiently agitate a collection of grains, you can turn them into a granular gas. And there's been a huge amount of work in a very large literature and some very interesting mathematics, some of which even compares reasonably well to experiment, certain limit, on the kinetic theory of these granular gases. You might say, well, this is really kind of like the gas in this room, just bigger, and just that the grains dissipate energy when they hit, and people have basically tried that approach with some success. On the other regime, the other end of the spectrum is the, I think it's a little picture from Bob Behringer's beautiful work here on solid piles, where grains are undergoing enduring contacts in a given situation. So here's, for example, a pile of little disks, and each of those disks essentially birefringent under stress. If you put it between cross polarizers, you can see which particles are stressed, and which particles are stressed turns out to be a very interesting problem in granular materials. And the particles that are stressed are not uniformly distributed throughout the material, but are in fact occur along these kind of complex networks of what people call force chains. This is a good solid pile, meaning that if I took this and I tilted it, it would not flow until a critical stress had been exceeded. So it's a solid. And you can even form fluid-like systems where, for example, what you're looking at here is a pan of a thin layer of sand, a couple grain diameters, I guess several grain diameters thick, I think 100 micron powder, 100 micron sand, and you're shaking it up and down and towing a rod through, and you can see a very pretty shock wave that's developed. It turns out to be well described by shallow water theory, this shock. So you get weights. Okay. And here's sort of a summary, which I think, I don't know if it's useful or not, but it's sort of how I tend to think about these things. That in physics, we tend to focus on sort of the particle level interactions. And we tend to kind of think in fundamental models, be it force chains, be it sort of hydrodynamic phenomena associated with multi-particle systems, jamming phenomena related to sort of critical phenomena ideas. There's an entire world of people who thought deeply and for a long time on these kind of granular problems, and they're soil mechanicians and geotechnical engineers. And the job of a soil mechanician or a geotechnical engineer has traditionally been, and still is, to make sure that accidents like these don't happen. So this is a liquefaction event after an earthquake in Japan, in which the material, the granular material under the buildings became like a fluid upon sufficient vibration, and these buildings fell over. And the sort of interesting bit for us is that there's been little detailed experiment modeling of what I'll call sustained or transient localized intrusion events. So a transient intrusion event would be simply drop an object into a granular material. A sustained intrusion event would be to sort of push your hand vigorously through a collection of grains sitting on the table. And these are exactly the problems that are interesting to us, and there's been not as much work on these kinds of problems. Okay, so that, I guess, ends the rather long overview, but before I continue onto a specific problem associated with granular material and a kind of sustained localized intrusion event, are there any questions? Yeah?
It's not a question, but I was just wondering, when you showed your cockroach,
Yeah.
so it had 6 legs.
Yeah.
So every time that it was moving, 2 was moving on this side and then 1 on this side.
Correct.
And then 2 on this side, 1 on this side.
Yeah.
So I think that's a good criteria to actually focus on, because when two legs are far apart from each other, then the granular, whatever, material around it is known as disturbed.
Yeah,
But when two close ones are moving, then you end up doing that swinging thing.
yeah.
So I was wondering if you actually focus on this criteria.
That's one of the interesting questions for sure. Questions of limb length and scaling of foot size relative to limb length, for sure. It turns out that that animal is a terrible runner on granular materials for reasons which we sort of suspect have to do with the fact that its feet are very small. At every footstep, it penetrates deeply to the ground and rubs its belly on the ground, and so it's basically dragging itself against the friction of its belly. The really good animals, the really good desert invertebrates that run really fast have very long limbs and larger feet and manage to keep their bodies off the ground. Yeah, so there's that. Okay, so the problem I'm going to tell you about is one that we've been looking at in a number of systems in the last several years, and that is the role of volume fraction, or how compact the granular medium is and its response to stresses. And I think this is a problem which probably doesn't have an analog in true fluids, and so I think it makes it kind of interesting. So, mechanics of shear response of a given granular material affected by the polydispersity, the distribution of grain sizes, grain shapes, friction between the grains, and something called volume fraction. And the volume fraction is defined as, in a collection of grains, in a container of grains, the solid volume of the grains divided by how much space they occupy. So, it turns out that in a typical pile of granular material, which I have here, they range in volume fraction from about 55% to about 64%, 64 being what people call random close packed, and 55% being sort of the loosest state of granular material one can make under Earth's gravity. That's one definition for it. And it turns out that these materials have very different response in how they respond to shear. And I want to show you a demo, which some of you might have seen, but I think illustrates the point very well on the role of compaction in the response of granular materials to shear. So, no one else has shown this demo like this, right? Good. Okay, so here I have a collection of sand, a granular material, and these aren't exactly, oops, if I can open it. These aren't exactly spheres, but they are, come up afterwards. See them, it's kind of like beach sand, which you find. And here I have a little beaker, and here I have nothing more. This is an old magician's trick, by the way, so, and I probably won't do it as well as an old magician, but you get the idea. Here I have just a bead chain, a rope chain, metal chain. And what I'm going to do is stick the chain in here, and I'm going to just simply pour the sand into this. And then I will do something which is maybe not so exciting. I will take it and I will pull it out of the sand. And you're not supposed to be necessarily amazed by that. But it turns out that the physics that goes on is rather interesting and complicated, and I would say not understood, so there's a problem right there. But I'm going to do something more interesting now. I'm going to pour it back in, and now instead of doing the standard magician, which is not to tell you what I've done, I'm just going to put the chain back in. Okay, no problem. And I'm going to pour, same identical setup, same granular material, and I'm going to pour it back in, and then I'm going to do the following. Get in there, and I'm going to hit, tap. I'm compacting. I'm increasing its volume fraction, the amount of solid volume occupied by the sand relative to the volume. So the volume of the sand is the same amount of volume that's occupied is decreasing, so my volume fraction is increasing, and I'm probably getting for 60%. Hopefully I won't break it, but you can see that it's gone down quite a bit. I don't know if you can see that. Let me just add a little bit more. Again. pull it out of this granular fluid. Now, if I'm brave. Oh. So, I've made a granular solid. Of course, it was a solid already, but so I'll pass this around, and if my talk is boring or incomprehensible, you can at least feel free to play with this. I'll start with it. But that experiment right there turns out to illustrate something which is very well known, the soil mechanicians, but from a fundamental physics point of view, or the point of view we need to understand how an animal moves, is a real interesting physics challenge and inspires the following experiment. But let me just sort of give you kind of a picture of what's going on and what the difference is in kind of, this is the cartoon sketch of what the difference is in granular materials that are loosely packed and closely packed when you subject them to a shear. And so here's what we're going to do. I'm going to take a box of grains. This is a loosely packed set of grains. There's 8 of them, and they are stacked in this way. Of course, in a real situation, they'd be in a random configuration, but this is just a cartoon picture. And it turns out that if I shear these by simply applying a force, for example, at the top here to the right, you can easily see that these grains will basically fall into these little gaps here, and the height of the granular system will increase, meaning that the system will have what's called consolidated. This delta H will be negative. In contrast, if I start with a closely packed collection of grains, meaning that the grains are all kind of nestled in the little nooks and cavities here, and I shear them again, the only way I can shear them is for these particles to kind of lift up a little bit over the adjacent particle, and it turns out that at the end of my simple shear experiment, I will have increased the height of my granular column, and that's called dilation. That's the word for it. And it turns out that Reynolds, same Reynolds as the fluid mechanics Reynolds, is the first one to kind of appreciate this, and he used it to explain this beautiful phenomenon, which I'm sure you've seen. This is my student walking on the beach. She studies turtles and decided she would just give us a nice video. And you can see that around her foot, the sand seems to be drying out. It turns out it's not really drying out. Dilation, basically as she shears this tightly, this compact granular material, basically causes the grains to expand, and that expanded grains then pulls the water into the pores and pulls it below ground and makes it look like it's drying out, and you can see that it recovers as the stress goes away from the material. So this is sort of a basic phenomena. And it turns out that this has interesting consequences in what happens when you do sort of the basic shearing of a granular material. So here the setup is the following, and we need this for the kind of experiments that I'm going to talk about next, so just bear with. We apply a normal load N, and we shear with a force T, and we shear over a distance S, and these plates are free to move. And it turns out that the granular material in the 2 different regimes, closely packed and loosely packed, displays rather different behavior. And it turns out that that behavior is the source of the interesting demo that I showed. In a tightly packed material, it turns out that for small s, for small deformations of the shear cell, the force basically increases linearly with s. So I'm controlling s, remember, and measuring t. Yes. Increases linearly with s. And in fact, if I decrease the displacement, I can just go back and forth along this curve. It displays just basically elastic response until I reach a point which is called the failure point, at which point the force it takes to shear this a given distance starts to decrease and asymptotes to a force T infinity. Call it here. In contrast, in a loosely packed collection of grains, the force continuously increases as the material consolidates as I shear it, but also turns out to reach this same line. And the kind of basic picture that happens here is the following. And basically, when I shear a tightly packed collection of granular material, it turns out that in order to shear it, I need to dilate. And that dilated material is a little bit weaker than the surrounding material. If it weren't, that was a smaller volume fraction, and the smaller volume fraction, the easier it is to move the grains past each other. And so it turns out that in a tightly packed collection of granular material, the dilation accompanies the shear, and all the shear is essentially localized in a small region. Whereas in a loosely packed collection of grains, as I shear the material, as it shears along a particular plane here, that material is stronger, and any subsequent shear is then propagated out into the bulk, which is weaker material. So the shear spreads throughout the material, and so that's the thing to keep in mind. In a tightly packed or closely packed collection of grains, you basically have a localization of the shear in these materials. Shear is confined to a thin region. Okay, and so here's the sort of story that I want to tell you about our studies of drag in loosely and closely packed granular material, and this is basically the work of my student Nick Gravish, collaborator Paul Ummenauer, and this was a paper last year. And the setup's the following. We have a localized intrusion, we have a granular bed, which happens to be 0.25 millimeter spherical glass particles with some polydispersity, about 15–20% polydispersity. They're all pretty much reasonable spheres. We take a plate, which I've only drawn a projection of this, but it's basically a 3 centimeter wide plate. We insert it into the granular material, and we apply constant speed loading of the plate. We just simply drag the plate into the material, and we use a load cell to measure the force, the resistance force on the plate as we drag it through. And the nice thing is that we can control the volume fraction of the material. And how do we do that? Well, we use what's called a fluidized bed, which I'll explain now. We have an airflow, which comes from some air pumps, and it encounters a flow distributor, which then homogenizes the flow and allows it to move through this granular material uniformly over the length of the bed. And it looks kind of like this. It looks like this. Here's a stepper motor, which is driving the system. Here's the load cell. Here's the plate. Here's the bed. So you can see, in fact, the plate is for some reason oriented in the wrong direction, but the plate is much narrower than the size of the bed. And here's what the experiment looks like. You simply take the plate and you pull it through, and the poppy seeds are there just to kind of show you how the material is flowing. What you get is, of course, the flow of material as this plate is dragged through the bed. Show it one more time. This is the loosely packed granular material. So what you see is that the material is lifted up in front of the plate, and then sort of lifted up all through here, and then sort of falls around the side.
It's like a Dow shock.
Yeah, a little bit. Okay, so that's what we do. Well, the other sort of feature that we can do is we can control the speed of the motor. We can control the depth at which we penetrate the plate, but we can also control the volume fraction. Here's the technique we use. This is a bed that was another bed that was built by my student Chen. This happens to be a bunch of poppy seeds. And what he does is he puts a bunch of leaf blowers behind this bed. You can't see them here. And there's a porous piece of material here, a porous plate, whose holes are small enough so the grains can't fall through, but the air can move through. And this functions as a flow distributor to make a uniform flow across the bed. And above a critical flow rate, the weight of the grains is balanced by the pressure drop of the air through this resistive granular material, and you have what's called the fluidization condition. And that fluidization condition then, in this case, leads to a state where the grains are all sort of moving around in the bed, and the bed happens to be bubbling. There's a famous bubbling instability, these things we won't talk about. But the bottom line is that from this, we can then do a trick where we, which I'll explain now. So, let's get this plot. Basically, from the height of the bed, we can then measure the compaction of the granular material. Okay? And so what we do is we attach a motor to the side of our bed and flow air up through the granular material, turn off the airflow, the grains settle into a loosely packed configuration, and then it turns out that if you attach a vibrating motor to the side of your structure, if you turn on the motor for a certain amount of time, the more time you turn on the motor, just like tapping your cereal box, the more it compacts the granular material. So if we want a state which is 61%, we just turn on for 2 seconds. If we want a state which is close to 62, we turn it on for 8 seconds, and so on and so forth. So that we can control the volume fraction precisely and repeatably. And these error bars are giving an indication of, if you do it a couple times, what sort of spread you have. This is the range. It doesn't look like a large tree.
Is that homogeneous in depth?
Yes, it is homogeneous in depth. We've checked that. Yeah. We didn't expect it to be, but it just turns out it is, and that's good for what I'll tell you next.
There's really a critical time.
Yeah, there is. Well, I mean, it looks like what you're saying, I think, is that for under 2 seconds it's fast, but there's large changes in volume fraction for changes in time, and for after 2 seconds or so, that not much happens.
I was sort of thinking in the first half a second, nothing happened.
Yeah, I'm not sure why nothing happened in the first half a second, actually.
What's the frequency of
The frequency is probably 60 RPM. It's really just a big motor with a piece of material which is asymmetric to the shaft and just serves to. It turns out that you can basically vibrate it in any way. So maybe you're not spinning it up enough at this point. That's a good question. I don't know why.
that's 1 per second, so that's right around.
Yeah, maybe that's it. Maybe that's it. I'll have to ask Nick to make sure. But the bottom line is that you can control the volume fraction quite well. And we use this trick all the time. The other way you can do it is you can basically take the blowers to the fluidized bed, you can pulse the air once per second or so, and repeated pulses tend to settle the material into a more compact state. And this is just a faster way. And the sort of interesting secret to this is that what you do is you actually turn on the airflow a little bit. And turning on the airflow a little bit below the onset of fluidization has an effect to basically reduce the friction between the grains, and that makes the material compact much faster. But the bottom line is you can control the volume fraction, and then you can do things like go back and measure the force as you drag at different speeds. And so here's what we did. We did that, and measure the average force as a function of volume fraction, and it's not so interesting. As the material becomes more compact, the force increases, and it increases monotonically and maybe linearly with the increasing volume fraction. But something much more interesting emerges if you look carefully, or even just look at the details of the force as a function of time. And that's what this plot shows. This is the force as a function of time experienced by the probe, by the plate, for 3 different volume fractions: 58, 60, and 62%. And see that for 58%, the force is basically constant as a function of time with small fluctuations. For 62%, there's large amplitude fluctuations in the force, top of this mean, which is higher. And for 60%, there's still these fluctuations, but they're not as dramatic. They're smaller. And you can do one more thing. You can measure, because as you might expect, this is going to have something to do with the dilation of the material, the change in state of the material. You can do a nice trick, which is to measure the actually compaction of the material pre and post experiment. And what you do is you essentially shine a laser sheet down on your granular bed, and then you move the laser sheet across the bed. So this is just a schematic showing a plate which has made this nice pile of material. And you take this laser sheet and you raster it across the bed, and if you stare at it at an oblique angle with a camera, it turns out that then changes in height of this map to changes in position on the camera, and you can resolve the surface profile of your granular bed. This is a standard trick. And so this is one particular scan, and this is a scan which has been rendered in 3D. And so then, knowing this, you can then calculate the change in volume of the bed before and after your drag experiment. Is that clear? Because that's sort of the most important. Those are the 2 important measurements. And so then you can plot these things, and this is a complicated plot, but let me just sort of walk you through it, because I like this a lot. Here we're plotting basically the root mean square of those force fluctuations as a function of volume fraction. on the top plot here, and here we're plotting basically the change in volume of the material pre and post experiment. And what you see is that for low volume fraction, below what is called is 0 here, which is phi minus, well, just some number, which I'll explain in a second, you see that the force fluctuations are small, and they essentially turn on at this point here. And it turns out that that point is exactly the point where the material goes from compacting, meaning that its volume is shrunk after the drag experiment, to have dilated, where the volume is now, the material has been pushed apart. And it's precisely that point that these fluctuations turn on. And so this is basically the dilation transition. Okay? And it turns out that you can do this at different speeds and nothing much changes. So really what this says is that there is a length scale, which is important here because there's a lack of speed. And so here is 2, 4, 6, and 8. And it turns out that the mean drag force is also independent, approximately independent of speed. And this is a feature which we'll see again in our discussions of intrusion in granular materials and the regime we're interested in, that the forces are dominated largely by the friction among the grains, and the friction between the grains and the intruder, and frictional forces tend to be speed independent. So whether I drag a millimeter a second through granular material or 10 centimeters a second, it turns out that forces are largely independent of speeds. Okay? Well, we can examine what's going on actually at the surface, because that reveals something kind of pretty. So on the left is again a video which I played earlier, showing basically this sort of deformation of the material. As I drag here, we've rigged the experiment to make it a little more dramatic, where we in fact have a little kind of T-shape which is being dragged on the plate. You can drag a plate through and you see the same thing. And on the right, now I will look at the surface, perform the same experiment, but in a material which is closely packed. And you see something which is quite different. You see nothing much happened, and at some point will pop up a ripple of material. And then nothing much happened, and poof, pops up. It doesn't make that sound. It's just sorry, I had to write it down. And again, so there's a qualitative change in the flow properties of the material when you go above and below this dilation transition. And what's going on? Well, this is the picture covered. But what we can do is then we can't look into the material at this point, or we weren't able to at this point. So what we did was sort of the next best thing. We take our plate and we shove it up against the plastic sidewall, a transparent wall, and we basically seed the flow, we seed the particles here with poppy seeds. This happen to be poppy seeds and tracers, we're more sophisticated now. And we can then essentially watch what goes on inside the material as the plate is dragging through the material. And just to convince you that that's not a crazy thing to do, here's the force measured in the original experiment. It goes up and then you see these oscillations. And here's the force measured in this kind of half experiment. And you see that the force is basically half because you're essentially, turns out, shoving about half the amount of material. But you see that this length scale, this lambda between these ripples is unchanged. Okay? Well, let me show you then what goes on in the flow in these two different situations. So the first is I'll play a video for the flow on loosely packed, and the second will be closely packed. And here's what it looks like from the side of loosely packed. And this is a cool video. And you can see, I'll let this play a couple times. You can see that, again, of course, you're shoving material up, you're lifting material up as you're moving forward. But you can see all the way out here, there's little kind of micro movements of material as you're dragging this plate. So everybody got that picture in the head, because I want to contrast it with the picture in the closely packed material. Which is quite different. And so what you see here is that in the closely packed material, you essentially transport a kind of wedge or block of material up a hill repeatedly. So there goes one, there goes another, there goes a third, here's a fourth, and 1, 2, 3, 4. And if you look when the first wedge starts, if you look over here, absolutely nothing is happening. And so really what you can sort of, from a take-home for this, is that these two materials in the loosely packed state is behaving more or less more like a fluid in its response to the intrusion, whereas the closely packed material is behaving more like a fracturing solid in response to the intrusion. Okay, so we can quantify this, and it turns out, I won't go into details, but I'm sure you've heard about PIV in the last couple of weeks. You can do a kind of granular PIV using open source PIV software. And you can then essentially, by cross-correlating images, resolve the flow of the material, the flow profile of the material. And here's what it looks like at 2 instants in time. Here's the plate. The velocity here is color-coded by the speed as well. So the arrows give you a sense of the direction of the flow. The color gives you the magnitude. And you can see that basically, in both cases, you have flow which is essentially up and to the right, but this extends further than on the right-hand side. Here you have a very sharp boundary between no flow and no flow. And you can do a kind of interesting plot. How long, by the way, when should I take?
Yeah, about 10 minutes.
Okay. You can visualize the flow during the drag, and you see that, for example, you take a cross-section here, a cut here, and you can then essentially plot the velocity as a function of time, and you see that it's composed of lots of kind of rapid oscillation as material far away from the plate starts to move and then stops to move, and starts to move and stops to move, starts to move and stops to move. This is easier to understand when contrasted, well, when I show you the video, this is what this kind of looks like. Here you can see the sort of material. It's in fact nearly impossible to see, unless you look at what I'll show you next, which is the case for closely packed material, in which what you see is that basically this front is essentially pinned as a function of time, and then pops out, and pinned and pops out, and so if I show you the video, it becomes, I think, more clear. There it is, and then pop out. And so basically, this front is essentially pinned in time, and then a new front emerges, and a new front is continuous process. Okay. So I can also tell you that the force and the flow are correlated. So below the critical volume fraction of which dilation occurs, basically the angle of this flow, the average angle of the flow, fluctuates rapidly, and the force fluctuates rapidly. And above this onset, this critical volume fraction, the angle of the wedge increases, and then suddenly, you'll see this in a second, drop as the force drops, and then starts to build back up. And I'll just let this play, because this is sort of the most important, bit here. So here the angle of the wedge is increasing, so the material is being up. This is during the material is being uplifted. And at some point, it says I'm no longer going to be uplifted here along this wedge. I'm going to break out a new wedge over here.
I mean, as it's pushing along, you're kind of piling more and more material above the subsurface, right?
You are.
So you're increasing the gravitational load.
Well, let me get to it. We have a little model which sort of predicts the right-hand side. So we don't understand really at all the left-hand side. It's a really complicated dynamics on the left-hand side for reasons which will become clear, I hope, in 10 minutes. On the right-hand side, it's a little bit simpler to think about. We have some understanding of that. But this is the kind of picture here, that the force and the flow are correlated. And that when the force suddenly drops, basically you see the angle of this wedge drop. And that's when you see a new one of these bands nucleated. Yes?
And as the volume fraction gets bigger, this
Yeah.
wedge gets bigger?
Yes, that's right.
Okay.
As the-
And the left looks as if what it's trying to do is what it's doing on the right.
Yeah.
But it's too fluid, so it keeps.
Yeah,
dropping,
that's exactly
right?
it. Yeah, it's a sort of, it's a frustrated attempt to do this. And let me get to our little model, and I think it'll be more clear. But that's the kind of basic picture that goes on. Now, it turns out that we haven't we understand, we think a little bit about this stuff here. And it takes advantage of something that I told you several slides back. The fact that in these consolidated materials, once I shear, once the material fractures, it's in a lower volume fraction. So it's looser there, it's weaker there. And so if I continue to shear, it's just going to stay in that, it's just going to shear in that region. That's the easiest place for the system to shear, so it'll just stay shearing that way. In the loosely packed material, things are more complicated because as I shear, the material becomes more consolidated in that little region which developed the shear, and then stronger, and so the system tries to pick another region to shear it, that's roughly speaking. And so here's the picture. Like Mike was saying, basically our model is the following. Consider a force. So what do we have here? We basically, and this is kind of the interesting feature, this is why I wanted to talk about this. This is the interesting feature of these dense granular flows in consolidated state, is that essentially the flow separates into two kind of solid chunks of material separated by a very thin fluid layer. Very different than a loosely packed state, very different than a fluid. And so the model is basically take a block, a wedge, take a wedge of mass M, and shove it up a hill of angle theta. And it's going to be shoved up a hill subject to the following forces. Of course, the weight of the block. There's going to be a friction force, which is the friction of this wedge of material against this other wedge of material, which is sand. There is a normal force, and that normal force is, of course, this direction. And then the friction is going to be UN. And that normal force has two components. One, of course, is the component of the weight, and the other is the component of the force that I'm actually shoving it into that way. So it's sort of a weird inclined plane problem, which we don't normally think of. In my mechanics class, I don't normally talk about. You're shoving your kind of doorstep against the thing. So, okay, what you do, you can compute for a given d, which is the distance your plate is into the material, the given width of the plate. You can compute the mass of this block if the angle is at angle theta, and it looks something like this. You can then essentially compute the force it takes to shove a wedge of this material up the plane here without acceleration, so you're balancing the forces at all time. And you can basically compute this. This is a little formula that says for a wedge inclined at an angle theta, and with a friction coefficient u between these two blocks, this is the force that it would take to move this material up the wedge. Okay? And you can plot these out, and they're kind of interesting. For zero angle, essentially you diverge because you're shoving an infinite amount of mass down the thing, and for a certain angle, which is I think 1 over mu, you also diverge, because it's basically impossible to move that material up anymore. And so you have a minimum in the force it takes to move a block of material up the hill. And our assumption here is that when this material starts to shear, when it breaks, the material in the slip plane dilates to a critical volume fraction. It's volume, well, in fact, I think I forgot to say, it turns out that when you shear a loosely packed material, eventually that material reaches what's called this critical volume fraction. When you shear a closely packed material, that material also reaches the critical volume fraction. And those happen to be the same state. That's one assumption. And the other assumption we make, which is sort of reasonable, is that with increasing volume fraction, this friction coefficient increases. And so you get a family of curves like this. Each of these is for a different friction coefficient. And then the model is the following. At time A, or at some point A, I basically break a new shear plane, and I'm running out of time. I may have to finish this tomorrow. That's the signal. Okay, let me keep going. Yeah, let me finish the thought, and then we'll quit. You break a new shear plane. Now, you've created this shear plane in bulk material, which has a force here at this minimum force. We're assuming that the system always finds a minimum force. You essentially then dilate this material. So now, because it's shearing, and the dilated material now is easier to push against. So the friction coefficient decreases. And now as I increase my, sorry, this is brushing this too much and I forgot to tell you certain things. As I increase, as I push the material, as I push the plate into the material, it turns out that something that we observe, which is just an observation, is that the bottom of this band is pinned to the bottom of the plate. The top seems to be pinned to the top surface of the material. So essentially this angle starts to increase. And as this angle increases, the force that is required to move this plate, move this chunk of material increases. And at some point though, that force reaches the value that is the same value that is the same force to create a new shear plane in the bulk. And so the system then hops to this new curve. And so here's the sort of picture, and here's the kind of model. And what you can see is we're plotting force on this axis and data on this axis before I just showed you these plots. And you see the force basically increases as the angle increases as you're shoving the material up until it's too hard to shove it up the plane. And the system says, well, there's a lower force. It's easier to break out further into the material. And that's what it does. So it basically cycles around this curve. So we'll go one more time. And it says, okay, it's easier to go here, and it pops over here. And that's our sort of picture of how these things are continuously breaking. And you're continuously doing this because you're always moving your plow into new material. Okay, we don't understand the loose pack, but let me just then conclude and say that the dilation transition granular media controls the flow and force response to drag. Loose pack granular material strengthens and compacts under shear. The closed pack material weakens and dilates. And the weakened shear planes are stable because that's the easiest place to move. And the periodic nucleation gives rise to large force fluctuations, and these are non-hydrodynamic behaviors, I would say. You must understand heterogeneous evolution of phi during localized perturbation. And I think I will close there today and take any questions, and we'll start on sand swimming tomorrow.
Is there a way you could visualize the force chains using something like what Bob Berenger did with like some sort of Peterson particles or something like that?
Yeah, if you did this in 2D, I guess.
Right, sure.
Yeah, we haven't done it 2D. And 3D. Tomorrow I'll tell you about how modeling approaches this, in which we think we can get some estimate of those kind of features from a discrete element computer models. Yeah.
So when in the loose pack, when you're driving through it,
Yeah.
you say it's really complicated because there's all these fluctuations.
Yeah.
But what if you did a time average, flow fields or force? Do you think it would simplify into something else?
Well, I mean, the time average would give you a picture which I think looks, you know, the average behavior is sort of like this. That's after we decided to give you time average to look like this, but smoother. Really, the issue is that in the loosely packed states, as soon as you form a shear plane, as soon as you sort of localize your shear, that material is stronger, right? And so now the system says, well, geez, there's an easier place to shear, and so it finds a different spot. And then that place is stronger. And so, you know, but it's complicated because now that stuff that you sheared is now included in the volume of which you move. So I think it's harder to understand. The closely packed is nice because it essentially just separates into two states, and in fact you can use what Coulomb developed as his method of wedges, which is essentially what we've done here to kind of figure out the forces.
Any others? Okay.